Hello students, welcome to this lecture number 4 on ionic equilibrium. In this lecture we are going to discuss three very important things. That is, number 1, we are going to discuss, that is the polyprotic acid. Or it is called polybasic acid, and we will discuss the polyacidic base. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. What is polyprotic acid? Let us first understand. So far, we have come across different types of acid like HCl, HBr, HI. All those acid will produce on dissociation in the aqueous solution. It will going to produce the 1H plus ion. Okay, but there are some acid like this H2SO4, H3PO4, H2CO3. All those acid you will see they have the more than one hydrogen, acidable hydrogen, and this acid is going to produce more than one hydrogen. These acids are called the polyprotic acid or polybasic acids. So we can define this polybasic acid like this, that this acid is going to produce more than one hydrogen, means more than one proton. That is why it is called polyprotic, that it will give more than one proton. It can give 2 protons, it can give 3 protons, accordingly it will be named. Diprotic acid, if it is able to give the 2 hydrogen atoms, 2 hydrogen ions, it will go to, this is a diprotic, this is triprotic, and this is also a diprotic acid. So what will be the difference between these HCl, HBr, where you will get the 1 hydrogen atom? Basically you will see in these acids they will produce the 2 hydrogen atom in the steps. So let us take one general polyprotic acid, diprotic acid, it is H2X. When it is ionizes in aqueous solution, you will find it will produce the 2H plus ion in steps. In the first steps you will find this will create this HX. All are in the aqueous solution. You have to write this is in the aqueous solution. So this is the first step where 1 hydrogen atom has been liberated by this acid. So in this case you will see this is a dissociation constant, first dissociation constant. A1 is the first dissociation constant. Dissociation constant. Okay. Then you have second dissociation. Next, this remaining part will be dissociated and it will again produce 1 hydrogen atom. You will find this will be ionized in like this fashion, And in this case, you will find that Ka2, that is a second dissociation constant. Second constant. So this is the first dissociation constant, second dissociation constant. If we take the overall reaction, overall dissociation of this acid, that will be this, and we are assuming in the first step of itself there will be a production of the two hydrogen atom, and in this case we will say Ka, that is the dissociation constant, overall dissociation constant. And you can see, you can write this first dissociation constant Ka1 is like this, concentration of H plus instead of concentration of H minus, Hx minus, and this H plus. Ka2 you will find that it will be, again one hydrogen has been produced, and it will be here, you have to H2x, here you find Hx. So this is a successive dissociation constant of this acid, and when we multiply this Ka1 into Ka2, it will going to create this and this is basically, you can find, this is the dissociation constant for the overall reaction. So we can write this very important note equation, that is this. So two successive dissociations, if we multiply the two successive dissociation constant, we will get the overall dissociation constant. So this is how the polyprotic acid behaves, and it will have the simple dissociation constant. So for the H3PO4, it will have the three dissociation constant. H3PO4 will have the three dissociation constant, Ka1, Ka2 and Ka3. And what will be the value of this dissociation constant? First, second or third, whether they will be same or different, that you can easily able to understand that when the hydrogen ion has been detached, hydrogen ion is ionized from this neutral molecule. This is a neutral molecule, it do not have any charge, so it can be easily be dissociated. But when it is becoming negative ion, then from this, when we are going to extract another plus ion, H plus ion, then it will create that difficulty in removing this. There will be resistance. So you have to give some lot of energy. So in this case, Ka2, the second dissociation constant will be higher than, in terms higher means that its value will be lower, because higher the dissociation constant means there will be higher the probability of ionization, right? So in this case, Ka1 is always greater than K2, K2 will be always greater than K3. So dissociation constant depends on in which stage this dissociation is being carried out. This is in the first steps from the neutral molecules, or this is the second step from the charged ions. So that is the thing that is all for this polyprotic acid. Okay, and this polyprotic acid is called diprotic, triprotic, depending on how much H plus ion is going to liberate. Now we are going to discuss another very important thing in your ionic equilibrium chapter, that is the ionic product of water. Water is a substance that acts as the acid or a base. Suppose water is being reacted with NH3, it will going to produce the ammonium hydroxide. At that time, water acts as a base. Water acts as a acid. When water reacts with HCl, it is going to produce at that time water acts as a base. So water can be acid or can be base. When water is self-ionizes means that it will automatically be ionizes. At that time, what we find, two molecules of water suppose, and it is one molecule will give the H plus ion and another molecule will take up this H plus ion. So it is going to produce this hydronium ion and the OH minus ion. So you can see one molecule acts as an acid, other molecule acts as base, and their conjugate acid, this acid have the conjugate base, this is conjugate base, and this base have the conjugate acid, this. So we see that water molecule self-ionizes, but their self-ionization process is very little, that we will understand now, and this is called the autoprotolysis. Autoprotolysis means automatically there and this phenomena is called the amphoteric because they are act as an acid and act as a base also, depending on the reagents, other reagents. So this ionization process is called the photolysis, and we can simplify this dissociation of the H2O in this fashion. H2O that is going to produce this hydrogen atom and OH minus atom, and the equilibrium constant K we will get the concentration of H plus and concentration of OH minus divided by the molar concentration of H2O. As H2O in excess amount, its molar concentration do not change with the time, so we can write K into concentration of H2O, that will itself a constant Kw, and it will give a product of the molar concentration of hydrogen ion and OH minus ion. This is called the ionic product that we are now discussing this. So ionic product is basically the product of the concentration, molar concentration of hydrogen ion and the molar concentration of the OH minus ion. This is called ionic product. And this ionic product, AW, depends on the temperature. How it depends on the temperature? When it is higher temperature, then what is going to happen? The dissociation will be increases. Ionization of the water will increases and it will going to produce more ions. So at that time, its Kw will change. When it is at the lower temperature, its Kw also will going to change. Now we discuss this, that at 25 degrees Celsius, when at 25 degrees Celsius is the room temperature, suppose at 25 degrees Celsius, the molar concentration of H plus ion has been found out 10 to the power 7 moles per liter, and the OH minus ion, it is having 10 to the power minus mole per liter at 25 degrees Celsius. So Kw, we can write this Kw, ionic product is basically, that is 10 to the power 7 into 10 to the power 7, it will be coming around 10 to the power minus 14, and it is at temperature 25 degrees Celsius. But if we increase the temperature to at 60 degrees Celsius, then we will get the Kw will be is equal to 10 to the power minus 13, and when it is at the temperature 0 degrees Celsius, this Kw is going to be different figure, that is 10 to the power minus 15. So you can see how Kw is changes with the temperature. If we increase the temperature, then dissociation will increase, and it will going to give the more amount of the H plus ion and OH minus ion, and that will give the different value of Kw. So whenever we talk about the Kw, we have to always mention this temperature. Another thing that is very important, to now understand what is Kw. Kw is basically the molar concentration of the hydrogen ion and the product of the molar concentration of hydrogen ion and the OH minus ion, and it is 24 as 25 degrees Celsius. But this Kw is fixed for any type of solutions, whether it is neutral solutions, or it is acidic solution or the basic solutions. Depending on this, we can say that is a very important thing, that Kw is constant, and with the help of this Kw, we can able to derive many things that we will discuss in later. And now we calculate the dissociation constant of water, of H2 from this equilibrium, that is H2O, it will going to produce H plus and OH minus. So you will see dissociation constant K is basically the molar concentration of H plus and the molar concentration of the OH minus divided by molar concentration of H2O. At 25 degrees Celsius, we know, at 25 degrees Celsius, we know molar concentration of H plus is equal to molar concentration of the OH minus, because it is a neutral solution. It will be 10 to the power 7 moles per liter. And the H2O, molar concentration of H2O is basically, we know that water has the density of 1 gram per cc. So 1 liter will have the mass will be 1000 gram, and we know molar mass of the water is 18. So it will be coming around 55.5. So we just put this value, of this molar concentration, that is 10 to the power minus 7 into 10 to the power minus 7 divided by 55.5, and you will get a value of 1.8 into 10 to the power minus. So from this we will get a value of 1.8 into 10 to the power minus 16. Okay, this will be dissociation constant of the water, means this value is very high, very low. And for this we can say the reaction of this reaction will proceed on the backward direction, reverse direction. So dissociation will be very less. Now we are going to calculate the degree of dissociation. Degree of dissociation. Degree of dissociation is given by, that is, total number of moles dissociated, number of moles of H2O, dissociated, divided by the number of moles undissociated. Number of moles undissociated. So in this case, we put the value, that is 10 to the power minus 7 divided by 55.5, and it will coming around 1.8 into 10 to the power minus 9. So degree of dissociation you can see also very less. So this process, the self-ionization process of the H2 is very minute, very less. But it has some value that we will discuss later on when we are going to establish the hydrolysis constant. At that time, this relationship is very helpful. Also, next video we will discuss about the pH. In this pH, we will understand how important this value is. So that is all for today's video. In this video, we have discussed about the polyprotic acid. We have discussed about the ionic product of the water. That is very important thing. And it will, from this ionic product of water, you will come to the pH. In the next video, we will discuss about it. That is all for today's video. And if you like this video, you can share with your friends. Thank you very much for watching. Thank you.